Chapter 5 is all about polynomials. We've been sort of working with polynomials so far, linear functions and quadratic functions, so lines and parabolas. We've been working with polynomials. Those are polynomials. In this chapter, we're getting into polynomials that have higher degrees than just 0, 1, or 2. Polynomials that have a degree of 3 or 4 or even 5, okay? And what those graphs look like and how do we work with those. It turns out that mathematically speaking, polynomials all have a lot of shared characteristics. And if you learn how to handle those shared characteristics, then you learn how functions behave in general. And that's a really good thing to know how to do. So, keep that in mind as we go through this chapter, because each of these little things that we're about to learn applies to every polynomial. First of all, we have some vocabulary as usual. What is a monomial? A monomial is a polynomial, but it's a special polynomial. Some of you are trying to tell me what that prefix right there means. What does mono mean? One. One. What? It's a polynomial with only one what? So you're thinking of polygon in geometry. This is not geometry. This is algebra. So we're talking about polynomials, equations. An equation, one term. Very good. So a monomial is one number or variable or a combination of a number and a variable as a single term. So it's an equation that has only one term, combination, C-O-M-B-I-N-A-T-I-O-N. So if that's what a monomial is, then what is a polynomial? Multiple. Could be multiple. You were thinking of tri. The prefix poly means many. Okay? So poly means many terms. Doesn't have to have many terms, but it could have many terms. So my definition is going to be a string of monomials put together by addition or subtraction. And I'm abbreviating addition and subtraction. So a polynomial has many terms. It could have one term, though. It could have 2 terms, 3 terms, 4 terms. It could have any number of terms. And each one of those terms is separated by addition or subtraction. We have some special polynomials that we need to talk about. There's monomial, obviously. We just talked about that one. One term. We have another one, binomial. What is a binomial? 2 terms. The prefix bi means 2. 2 terms. Like a biplane. 2 wings on that plane. We have another one, trinomial. How many terms there? 3. The prefix tri means 3, like a triangle. 3 terms. Okay? Anything beyond that, 4 terms, 5 terms, 6 terms, we just say that it's a 4-term polynomial or a 5-term polynomial. These 3 are the only ones that have special names to them. Okay, next definition, degree. What is the degree? In geometry, the measure of an angle, yeah. In science, it would be how warm it is outside, probably, right? But in algebra, the degree is the highest exponent. I'm putting a slash there because that's not quite a good definition. Generally, highest exponent, or the highest sum of exponents. Attached to variables. In the terms. of a polynomial. So it's the highest exponent in the term, or in the terms of the polynomials, or if you have more than one exponent in a term, you add the exponents together. The highest sum of the exponents attached to the variables in the terms of a polynomial gives you the degree. Whatever the highest number is that you get would be the degree. The leading coefficient is the number in front of the term with the highest degree. So if I ask you for the leading coefficient of the polynomial, you would have to go through and figure out all of the degrees of all of the terms. Whichever term has the highest degree, the number in front of that term is the leading coefficient, even if it's not in the first position in the equation. Finally, standard form of a polynomial. We're going to be working with standard form of a polynomial a lot. All terms are written from highest degree to lowest degree. So just a couple examples so that we can kind of understand what degree means. What is the degree of a squared? 2. What if I had a squared, b squared? What would the degree of that be? 4. Why is it 4 now? We add 2 plus 2. What if I had a squared, b squared, c to the third? What's the degree of that term now? 7. Okay, 2 plus 2 plus 3. What if this was my polynomial? A squared, b squared, c to the third plus b to the fifth. What is the degree of this polynomial? It's still 7. Because this term has a degree of 7. This term has a degree of 5. The degree of the polynomial is the degree of the term that is highest. This is the degree that is highest, 7. So therefore, this polynomial has a degree of 7. So if there was a 5 in front and this was a 3, what would the leading coefficient of this polynomial be? 5. Okay? Because this term has the highest degree, so therefore the leading coefficient must be 5.
So they all have to be multiplied together so you're able to add the degrees?
Yeah. Terms are separated by addition or subtraction. Okay? So this plus sign right here makes one term, 2 terms. If I were to put a c to the 10th, what is the degree of this polynomial now? 15, and the leading coefficient would be 3. No, if I was asking for the leading coefficient, you'd just say 3. Okay? If I was asking for the degree, you'd say 15. Okay? Let's see, degree. Okay, terms, standard form. Is this written in standard form? No, because this degree is higher than this degree. So if I was writing it in standard form, this term would have to move to here. Okay? Highest degree to lowest degree. Make sense? What is the degree of, if I put a plus 8 there, what's the degree of that term? It's 0. Why is it 0? Because there's no variable there. If I put an x on that, what's the degree of that term now? 1. Why? Why is it 1? Because the variable has an exponent of 1. Okay? So if you want, you can think of it as being an x there with a degree of 0 for that plus 8 that I had. So if I cover up the plus 8, if I get rid of that, okay, and I just have the plus 8, it's almost like I have plus 8x to the 0, which gives me that 0 degree. Make sense? Okay. So moving on. Standard form of a polynomial is that. It looks really complicated, but it's really not that bad. I just want to point out a couple things that are going on here. First of all, p of x. This is function notation. Why am I probably using the letter p? Yeah, it stands for polynomial. Okay, a polynomial is a function of x, which means x is my variable, equals. What is that saying right there? What does that say? No. It's not an exponent. What is that? Subscript. So I say, if I'm reading this, I say a sub n. Okay? Times x to the n plus a sub n minus 1 times x to the n minus 1. And so on until I get down to the second to last term, a sub 1 times x to the first plus a sub 0. Technically, I could write times x to the 0 here, but x to the 0 becomes 1 and it disappears, so I'm just left with that a sub 0, okay? So I want to point out the pattern that's going on here. This notation is just telling you that what's happening to the exponent each time in standard form. We have n, then we have n minus 1, then we'd have n minus 2, then n minus 3, then n minus, and so on, until you got down to just 1 and then 0, okay? Your exponents are just descending. The highest degree to the next highest degree to the next highest degree to the next highest degree, all the way down until you have just a constant sitting here. A sub 0 is a constant. This notation right here is just telling you that this is the number attached to the x to the nth power. This is the number attached to the x to the n minus 1 power, and so on. This is the number attached to the x to the first power. Okay? Don't get confused. I know it's the first time that you've seen this, so you probably are confused, but don't let the notation bog you down. We're going to work with this quite a bit. By the time we work with it a little bit, hopefully this notation here will make sense. It's just a way of calling something in general instead of just a specific number. For example, p of x equals 4x to the third plus 3x squared plus 5x minus 2. Notice that I have an exponent of 3, an exponent of 2, an exponent of 1, and then technically an exponent of 0. X to the 0 here, okay? Now, a to the n here, x to the n would be x to the third. A sub n would be that 4 sitting right there. A sub n minus 1 goes with the x to the n minus 1. N was 3 to begin with, so now we're at 2. So a sub 2 equals 3. A sub 3 equals 5. A sub 4 equals blah, blah, blah. Okay? I think I said that backwards, but that's okay. Don't get bogged down by the notation. We're just putting terms in order from highest degree to lowest. The leading coefficient in this problem would be what? 4. Okay? So, that's standard form. Typically, we talk about polynomials by mentioning either the degree or the number of terms. So I'll say, well, give me a third degree polynomial. As soon as I say, give me a third degree polynomial, I know that I'm looking for a polynomial that has a highest exponent of 3. Okay? Or if I say, give me a trinomial, then I'm talking about the number of terms that the polynomial has. It could have any degree I want, but it can only have how many terms? 3, if I'm talking about a trinomial. Okay? So that's what this is saying right here. A polynomial does not need to have every term accounted for. A polynomial also does not need to have multiple terms. It can have only one term. It can be a fifth degree polynomial with only one term. It can be a fifth degree polynomial with 5 terms. Okay? So this chart right here kind of illustrates that. First of all, I have degrees 0, 1, 2, 3, 4, and 5. I have the name for those types of degrees of polynomials. So if I have a 0 degree polynomial, that would be like p of x equals 2. That is called the constant. It's a constant polynomial. If I were to graph it, it would just be a horizontal line that goes through 2. A first degree polynomial is a linear polynomial. We've been working with linear polynomials ever since Algebra 1. Y equals 5x plus 1. The degree of that polynomial is 1. Okay, so that's a linear polynomial. Quadratic polynomial we've been working with a lot in this class so far. Y equals 3x squared plus 2x plus 1. Okay? If I were to graph it, it would make a parabola. I've been calling it a quadratic equation. It's a quadratic polynomial now. Still has a degree of 2. A third degree polynomial, we'll be working with those quite a bit in this class also. It's called a cubic polynomial. A fourth degree polynomial, we'll see some of those. That's called a quartic polynomial. And then a fifth degree polynomial is called a quintic polynomial. Polynomials that are higher than that, 6th degree, 7th degree, 8th degree, and so on, we won't refer to them using prefixes like this. We'll just call them a 6th degree polynomial, a 7th degree polynomial. And honestly, a 5th degree polynomial, a 4th degree polynomial, but after that, I'm going to call it cubic, quadratic, linear, and constant. Okay? So for example, for a 0 degree polynomial, 5 is a polynomial of 0 degree because there's no variable here. It's just a number. Okay? Constants have 0 degree. X plus 4 is a linear polynomial. If I graphed it, it would be a line that goes through 4 on the y-axis and has a slope of 1. Quadratic polynomial, 4x squared. Notice that there's only one term here. This is a parabola that has been stretched. A cubic polynomial, notice this time I have 3 terms. But notice, most importantly, that it's a 3rd degree polynomial. That's why it's a cubic. This one only has 2 terms, but the highest degree is 4, so that makes it a 4th degree polynomial, a quartic polynomial. And this one has 1, 2, 3, 4 terms. It's a 5th degree polynomial, which makes it a quintic polynomial. Once we start talking about the number of terms, then I start bringing in monomial, binomial, trinomial, and so on. So if I have 1 term only, that's a monomial. If I have 2 terms, that's a binomial. Again, 1 term, monomial. 3 terms, trinomial. 2 terms, binomial. 4 terms, and terms above 4, we're just going to say a polynomial of however many terms it is. So in this case, a polynomial of 4 terms. All right? So for these examples that are sitting right here, this is a 0 degree monomial. This one is a 1st degree binomial. This one is a 2nd degree, so a quadratic monomial. This one is a 3rd degree, so cubic trinomial. This one is 4th degree, so quartic, 2 terms, quartic binomial. And finally, 1, 2, 3, 4 terms, but it's a 5th degree, so quintic polynomial of 4 terms. So I could also say a 5th degree polynomial with 4 terms. There. All right, so let's take these 4 examples and classify our polynomials. It says write each polynomial in standard form, then classify each polynomial by its degree, leading coefficient, and number of terms. So we're going to try to use this vocabulary here. First of all, we need to write it in standard form. So for this first one, is it in standard form? No. What needs to go first? 9x squared. Then plus 3x plus 5. Now it's in standard form. The degree is descending from left to right. So we did that. Classify each polynomial by its degree, leading coefficient, and number of terms. What is the degree of this polynomial? 2. It's a 2nd degree polynomial. So degree is 2. So I could call it what? Q quadratic. Its leading coefficient is what? 9. And number of terms. There are 3 terms. So I could call this a trinomial. So this would be a quadratic trinomial. All right, the next one to the right. Is this one in standard form? No. By the way, what is the leading coefficient of this polynomial right now? 1. Very good, it's 1. It's 1 because the degree is 4. It's sitting right here. And the number attached to that is 1. So therefore the leading coefficient is 1, even though right now it's sitting in the middle. Okay? So be careful about that. All right, let's write this in standard form. X to the 4th Good. These are like terms right here, the 6x, the minus 6x squared and the 10x squared. So we have to combine those, and we get positive 4x squared. Okay, is it a minus 4x or a plus 4x? That's a positive 4 right there, so I'm going to write plus 4x. And then the minus 12. Now it's in standard form. All of our like terms are combined, so we're good to go. I need to talk about the degree. What is the degree? 4. So I could call this, what was the vocab word? Quartic. The leading coefficient we said was 1. And the number of terms? There are 4. So do I have a special word for this? 4-term polynomial? Binomial is 2 terms. No, it's just a 4-term polynomial basically. So I don't have a word for this, so it would just be a 4-term polynomial. So I'm just going to leave it at 4. Okay? Just 4. Yeah, it's a 4-term polynomial. If there's a special word for it, give me the special word. Okay, the third one. What should I write? Good? I need the degree. Is 4, so I could call that quartic. And then leading coefficient is 5. And then the terms? There are 3. Do I have a special word for that? Trinomial. Good. So that's a quartic trinomial. And the last one. Good. Negative 4x to the 5th. Yep. Plus 13. We're combining like terms as we go, and the sign goes with the term. That's a negative 4x to the 5th. So negative 4x to the 5th gets written out front. Okay, degree. Five. Do I have a special word for that one or no? Quintic. And leading coefficient. It's negative 4. And the number of terms? There's 3 terms here, so it's a quintic trinomial. That's all you got to do for these. 9 through 19 odd, what is that? 6 problems? Piece of cake. Like I said in the beginning of this section, all polynomials start to show the same type of behavior over and over and over again. So once we learn that behavior, we can start to form a picture in our minds of what the graphs of these things are going to look like before we even look at the graph, which is a really powerful thing to be able to do. So the graphs of your polynomial functions have a lot of shared characteristics. I have constant, linear, quadratic, cubic, quartic, and quintic functions sitting up here. They're all polynomials. All right? So what would the degree of this one be? 0. What's the degree of my linear function? 1. What's the degree of my quadratic function? 2. What's the degree of my cubic function? 3. And quartic? 4. And quintic? 5. Okay? So once we start looking at these functions in terms of their degree, we start to see some things. First of all, the constant function is what? What is that kind of graph? It's just a horizontal line, okay? That horizontal line could go through anywhere, but it's going to be a horizontal line if it's a constant function with a degree of 0. That's kind of a trivial one. We don't really care too much about that one as long as we remember that that's what it looks like. The important ones to know are these guys here. Your linear function forms a what? A line. Your quadratic function forms a what? Parabola. And we've studied these extensively in algebra. Algebra 1 and Algebra 2. Okay? Your cubic function makes a graph that more or less will look like this. Your quartic function makes a graph that looks more or less like this. And your quintic function makes a graph more or less that looks like that. Okay? There are some similarities in these graphs, though, even though they kind of look different. Does anybody see something that looks similar? You are on the right track, definitely. Look at my linear function. Where does it start? In this particular graph, where does it start? Starts down here, right? And ends up here. Look at my cubic function. Where does it start? Down here. And ends up here. Look at my quintic function. Where does it start? Down here and ends up here. Odd degrees. Odd degrees, you're right, look like this, basically. They start low and they end high. Or, down the road, start high and end low. Okay? So that's just like a little pattern that we can kind of see. What you're going to hear me say is that this is an odd degree polynomial. This is an odd degree polynomial. This one's an odd degree polynomial. So the graph is going to look more or less like a snake. It kind of snakes its way through. Okay? This one kind of snakes its way through. But more or less, overall, it kind of looks like a snake. That leaves the even degrees. What do you notice? Yes, they start and end in the same spot. So this one starts low, ends low. This one starts high, ends high. In between, some stuff happens. Okay? Overall, the general shape of this guy looks like a U. If I took this and I dragged it down a little bit, that's what you're saying?
No, like,
If I took this and bumped it down?
Yeah.
Yeah. Just the opposite way. Yeah. But overall, the general shape of this graph with an even degree looks like a U, okay? This U is upside down. This U is right side up, but it has a bump in it. Overall, your linear function, or your odd degree functions, so your linear, your cubic, your 5th degree, your 7th degree polynomials, and so on, they're all going to look like snakes. They might have a bump in it. They might have a few bumps in it. They might have no bumps at all in it. But in general, it's going to look like a snake. It'll start low and end high, or start high and end low. Okay? I also want to talk about the general form for equations that look like this. If this was a polynomial, p of x, your equation here would be p of x equals 3 halves. Why 3 halves? Yeah, that's where this line is going through the y-axis. So that would be your y-intercept. That's all you get. Horizontal line that goes through 3 halves. In general on this one, though, on this one it's just going to be some sort of constant. On this one in general, we have p of x equals, what's our general format for a linear equation in slope-intercept form? mx plus b, yeah. mx plus b. I'm using p of x because I'm saying it's a polynomial. What's the general form for a quadratic equation? P of x equals, before the x squared, you got x squared, but what's the letter in front? ax squared plus bx plus c. Okay, so I could have just called this p of x equals a. I could have called this p of x equals ax plus b. Then over here I have p of x equals ax squared plus bx plus c. So for a cubic polynomial, what is the general form for my polynomial? Ax to the third plus bx squared plus cx plus, very good. And for a quartic, p of x equals ax to the fourth plus bx to the third plus cx squared plus dx to the first, really, plus e. I'm not going to use e. E is already assigned, so let's call it f. E is its own number. The letter E is a number also in math, so I'm going to avoid using E on its own. No, it deals with exponential functions. E is its own number. It's like 2.71 something. Kind of like pi is 3.14. Quintic. P of x equals ax to the fifth plus, yep, good, yep, fx plus g. Okay, so you get the idea. We can assign letters to the coefficients on each one of those terms to generate the standard form for any one of these polynomials. Okay? It's just patterns. There's a lot of patterns in this chapter. And the sooner you start to see those patterns, the better off you're going to be. And here's one of your first patterns right here, how we generate standard form for polynomials. We're ready now for a couple more vocab words. End behavior and turning points. I've already kind of talked about end behavior, and I've already kind of talked about turning points, but let's get some official vocab down here. End behavior is what the graph does as x, this is kind of important here, as x goes to infinity and as x goes to negative infinity. Okay? I have an arrow there and I have the infinity symbol, but you read it as what the graph does as x goes to infinity and as x goes to negative infinity. I'll talk about that in a second too. Turn your paper sideways. Practice writing the infinity symbol. Okay, turning points are when the graph, changes direction. By changing direction, I mean it switches from increasing to decreasing. Or it could, if it was decreasing, switch to increasing. Okay? That's what it means by changes direction. So a turning point is where the graph kind of turns around and starts going the other way. So I just want to point out end behavior on these graphs now. The direction for end behavior was as x goes to infinity. So let's take a look at this guy right here. As x goes to infinity, that means as x gets bigger and bigger and bigger and bigger. What is the graph doing? It's going down for forever. Okay? As x gets infinitely more negative, so as x goes off in this direction, what is the graph doing? It's going down forever. On this one, as x becomes bigger and bigger and bigger, what is our graph doing? It's going up for forever. As x becomes infinitely more negative, as x goes off in this direction, what is our graph doing? Going down for forever. Okay, that's end behavior. What is the graph doing as x becomes infinitely big or infinitely negative? Make sense? On this one, as x becomes infinitely negative, what does our graph do? Goes up for forever. As x becomes infinitely bigger, the graph goes up for forever. Okay? That's end behavior. Turning points are where the graph turns around. So the function in this case is increasing, and it's always increasing. The function in this case is increasing here, and then it switches to decreasing. That switch right there is a turning point. This function is increasing here, and then it switches to decreasing, and then it's decreasing for a while, and then it switches to increasing, and then it increases for forever. Okay? This function has two turning points. This one, it happens, starts off decreasing, switches to increasing, switches to decreasing, switches to increasing, and then it increases for forever. Okay? This one happens to have three turning points. On this one, we are increasing here, and then we turn around and we start decreasing. What about right there? Is that a turning point? We are decreasing, and then we're still decreasing. So is this a turning point? No. Okay? But then there it turns around. So this one happens to only have two turning points. Okay, basically what amounts to a little bit more vocab here. All polynomial functions display end behavior. All of them do. And we need to know how to determine the end behavior of a function. It's easily found by looking at the degree. and the leading coefficient of any polynomial. Okay? The degree tells you if it's going to look like a snake or a U. The leading coefficient tells you if it's going to be increasing from, or starting low and ending high, or if it's going to be starting high and ending low, or if the U is going to be right side up, or if the U is going to be upside down. Okay? And we already know that from polynomials when we're working with quadratic functions. If we had a negative x squared, the U was upside down. Okay? The same thing applies to all polynomials. A function is increasing on the graph when the graph goes up from left to right. A function is decreasing when the graph goes down from left to right. Okay, so we have these four graphs right here. These are your general looking polynomials. Either you are, what degree would this be?
0. No, 3.
Or 2 or 4 or 6 or whatever, okay? I can't say for sure that it's 2, but I can say for sure that it's even. The leading coefficient here is positive because this is a U that points up. The end behavior here is as x goes to negative infinity, the graph goes up. As x goes to positive infinity, the graph goes up. So the end behavior is up to up. Okay? In this particular case, there's one turning point. The turning point is right there. There could be more. We are increasing in this interval right here. Have you guys learned interval notation yet? Well, the interval for increasing is going to be 0, infinity. Just get that written down. Basically what that means is when x is greater than 0, the function is increasing. In interval notation, it's going to be negative infinity, 0 for decreasing. And what that means is x is less than 0. And we'll finish up the rest next time.